All right, so we've talked about the pH scale. We've talked about how to calculate those pH values using negative log of, so on and so forth, and identifying through pH what a base, acid, or neutral substance is. What we're going to do now is talk a little bit about specific ways to look at acids and bases. In terms of these ideas that exist, there are some schools of thought where we have this, what we call Arrhenius acids and bases, and Bronsted-Lowry acids and bases. And it's really just ways to kind of identify what acids and bases are, how they act, so on and so forth, what they produce, so on and so forth. So when dissolved in water, acids usually produce what we call a hydronium ion, which is an H3O plus, and that's kind of like what we see as an H plus ion, that positive one charge up there. We can see because that's water that's basically gaining another H ion, right, an H plus ion there. So we see as HCl acts like an Arrhenius acid, really what's happening is what we see here to start is just splitting apart. So our acids are going to be just kind of what we call dissociating. So that's just splitting apart right here into its different components, which is the H plus ion, which designates an acid, and then the Cl minus ion, which is what it was attached to there. And really the same thing happens in the bases when they're dissolved in water. So when dissolved in water, bases produce a hydroxide ion that we talked about before. And hydroxide ions are just the OH with a -1 charge, right? The -1 comes at the end. So as an Arrhenius base, we see the two things that are the ions that form in solution or in water out of solution. For like a sodium hydroxide base is the Na ion and the OH ion. So when we're going through these, all we're doing is really splitting these up and getting them to dissociate, which means split apart into its ions. And these are all going to be freely in water. So they are going to be dissolved in water, which means they are all aqueous. So the state of matter should always be aqueous. So this is going to turn into a positive potassium ion, aqueous, plus the OH -1, which is aqueous. There's only one of each based on the formula given there. So we can see that that's an Arrhenius base right there because of that OH here. Now, if we want, we can say OH, those are our bases. And then whenever we have our H in front, that's going to be our Arrhenius acids, or an acid in general, where we're going to develop those hydrogen ions, right? Hydrogen ions and whatever it's attached to are just going to split up. So really all we're doing is taking the hydrogen and isolating it, the hydroxide and isolating it if it's a Arrhenius base, and just splitting it up. So here we have a +2. Now, because that barium is a +2 ion, that's why you see there's two hydroxide ions here. So what I'm going to do is, to make sure this is balanced, I know that barium hydroxide, this base, will actually create two hydroxide ions. So if I'm looking at like the number of OH -1s that I've developed here, there is only one, right? Here's the number of H plus ions, and to simplify, I'm just not going to include that charge. If I don't write a 1, that's understood. H plus, there's only one. The number of H pluses from this is 1. And then, of course, the number of OH ions here is actually 2 because of the 2 that were required to balance out the +2 charge of the barium. All right, so Bronsted-Lowry, aside from the Arrhenius idea, is kind of that acids actually donate protons, which are the H pluses. So these are proton donors. right, which produce conjugate bases. Now, conjugate base is a substance that loses H and becomes a little bit more basic, right? The more H's we have, the more acidic we are. So if an acid loses the H that it has because it produced or it donated it, it produces a conjugate base. So if H goes away to something else, we're left over with just the Cl, which means it's a conjugate base, right? We got more basic. If the H2s lose a proton, then a conjugate base, and again, it's only one proton, so one H ion, we end up with our conjugate base of HSO4. And of course, the same thing happens if the H gets donated or to something else, then we end up with NO3 as our conjugate base. And the same thing is true for bases on the opposite side. If acids that have the H plus ions are donors, then the bases that don't have the H plus ions to begin with are the acceptors. Right? So, of course, if they become, or if they accept another hydrogen ion, then that means that they become conjugate acids, which become more acidic. Right? So acids donate their protons to become more basic, effectively, and bases accept other hydrogen ions to become more acidic. So if I add a hydrogen to OH, then that becomes HOH, or more commonly referred to as H2O. Right? If I already have water and it's neutral, then I end up with an additional hydrogen if I'm adding a hydrogen to make those hydronium ions, which becomes more acidic. And then, of course, H and I would be my conjugate acid here. So as I'm going through, we can kind of just develop these conjugate acids and bases based on what's happening to the base. So the acid, remember, is going to donate a proton to whatever the base is, right? The acid donates the proton, the base takes it. The acid becomes more basic, so we call the acid that has a conjugate base, acid conjugate base, acid conjugate base, where we also then have the base becoming a conjugate acid based on accepting that hydrogen. So the conjugate acid is going to be NH4 with a +1 charge overall because it became more positive by 1 by adding that H plus ion, right? So these are just H pluses getting donated and accepted one way or the other. All right, which means that the conjugate base is going to be F minus 1 because the H was donated from the acid, right? Conjugate acid over here should be H2O because OH is gaining that hydrogen ion, and the acid, or the conjugate base, should be just the chlorine with a -1 charge because it lost its hydrogen. Again, this acid donates its to get a conjugate base of the CO3 -2. And now this becomes, again, one of those hydronium ions, H3O plus. So again, you get your conjugate pairs. So you're able to kind of identify, well, what's the acid to start? The acid is always the one that has the hydrogen ion in it first at the beginning. And then the base is going to be whatever is the opposite of that. So again, water, since it's neutral, can act as a base or an acid, which is why it's such a nifty substance.